Welcome back to our exploration of the frame budget approach. After our deep dive into quantum measurement, we're now tackling another, well, frankly bizarre quantum effect, tunneling. I mean, how on earth can a particle get to the other side of a barrier when it just doesn't have enough energy to climb over it?
All right, so here's our game plan. First, we're going to look at what makes tunneling feel like the impossible leap. Then, we'll check out the standard explanation, which we're calling the quantum wave. After that, we'll see how the frame budget approach asks a different question, leading us to the idea of paths and filters. And finally, we'll wrap it all up with 3 brand new takeaways.
First up, the impossible leap. You see, to really get why tunneling is so mind-bending, we have to start with just how much it messes with our everyday, common-sense view of the world. Okay, so picture this. You're rolling a ball towards a hill. If you don't give it enough of a push, enough speed, what happens? Well, it rolls partway up, and then it just rolls back down. Simple. That's our classical world. But in the quantum realm, things get weird. A particle faces an energy hill, and even without enough energy to make the climb, sometimes it just appears on the other side. That's quantum tunneling. And yeah, that's what makes this so baffling.
And you might be thinking this is just some weird theoretical quirk that physicists nerd out about, but no way. Tunneling is absolutely fundamental. It's the very process that lets nuclear fusion happen inside stars, allowing protons to get close enough to fuse despite their powerful repulsion. It's also right at the heart of technology we use every single day, from the flash memory in your phone to super precise scanning tunneling microscopes. What looks impossible in our big classical world is actually a critical part of how the universe ticks.
So what's the mainstream explanation for this? How do we account for it? Well, that brings us to part 2, the quantum wave. This is the standard and, let's be clear, incredibly successful way quantum mechanics makes sense of tunneling.
So the standard view says a particle isn't really a solid little point. It's more like a wave of probability, something called a wave function. This wave tells you where you're likely to find the particle. So before the barrier, the wave is strong. When it hits the barrier, it doesn't just crash and stop. Instead, it fades away really, really fast. It decays. But here's the kicker. If that barrier isn't infinitely thick, a tiny little piece of that wave, a tiny little ripple, actually survives and pops out on the other side. And that tiny wave means there's a small but very real chance that if you go and look for the particle, you'll just find it there.
Now, what's crucial here is that this doesn't actually violate any laws about energy. The particle never climbs the hill. It's not about that. Instead, its wave-like nature just means its location is uncertain. The math is simply a tool for calculating the odds, the probability of it being found on one side versus the other. And it's a framework that predicts these odds with absolutely incredible accuracy. So the standard explanation is fantastic at predicting that tunneling happens. But the frame budget approach, it's not just satisfied with the what. It wants to ask how in a completely different way. And this brings us to part 3, a different question. The goal here isn't to throw out the old mass, not at all. It's to reframe the entire problem. You see, the standard question, how does the particle get through the wall? Well, it kind of invites these weird images of some ghost phasing through a solid object. The FBA says, hold on, let's pivot. It takes a step back and asks something much more basic. Given the state of the entire system right now, what are the physically allowed next steps? What continuations are actually possible for this system's evolution? And remember from last time, this is core FBA thinking. It sees reality not as a smooth, flowing movie, but as a series of distinct frames, a sequence of updates, clicking from one moment to the next. So, for tunneling, the question isn't about some continuous journey through a wall. It's about what the next frame of reality is allowed to look like after the particle hits it. This leads us to a key FBA concept, the continuation option. And really, it's just any next step that's physically allowed. But what's so important here is that these options aren't set in stone. They depend on the real physical conditions. Things like how the parts of the system are coupled, what the boundaries are, and even the level of detail, the resolution at which we're describing everything. And this is where the FBA adds a really crucial layer. It says that not all possibilities are created equal. Just because a future state is possible doesn't mean it's probable, or stable, or easy to get to. Some outcomes are really robust, they're heavily supported, easy to achieve. But others are light, fragile, and they require everything to be just right for them to actually happen. So how does this whole idea of weighted possibilities change how we see tunneling? That brings us to our 4th section, paths, and filters. Let's really apply this FBA thinking directly to that particle and that barrier. And this slide right here brilliantly shows the conceptual shift. In the normal view, a barrier is a wall. It's an obstacle. Full stop. But in an FBA reading, that barrier acts more like a continuation filter. It's not just passively blocking something, it's an active part of the system's environment that shapes and constrains the whole set of available next steps. It literally changes the menu of what can happen next. So we can start to imagine a system's evolution as a bunch of branching paths into the future. Some of these future paths are really robust. You can think of them like a thick rope, a path bundle, made of tons of similar microscopic possibilities all leading to basically the same outcome. The system is super likely to go down this path. But other continuation paths, they're like a single thin thread. They're possible, sure, but only under very precise, very fragile conditions. And here it is. Here's the payoff. In this FBA reading, tunneling isn't some particle breaking the laws of physics. It's the entire system following one of its available but very, very thin future paths. The barrier, acting as a filter, makes the bounce-back path a thick, sturdy, easy-to-follow rope, but it leaves the tunnel-through path as a single, fragile thread. It's a possible continuation, just a very, very unlikely one. Now, it's really important to be clear about what this means. The FBA is not trying to go to war with the physics textbooks here. As the source material puts it, this is an FBA-compatible reading. It's a different interpretive lens. It suggests that maybe, just maybe, what we call quantum probability isn't just pure blind randomness. Maybe it's a measure of how stable or thick these different future paths are. It's a whole new way to think about what chance might actually mean at a deeper level. So let's bring this all home. Part 5. Let's pull out 3 key takeaways from looking at quantum tunneling through this FBA lens. Here's the shift in perspective, in a nutshell. First, we moved from asking the mysterious question of how a particle gets through a wall to asking the much more practical question of what continuation processes are physically available to the system. Second, we reframed the barrier from being a simple, solid obstacle to seeing it as an active filter that shapes the landscape of possibilities. And third, we opened up a new way to think about probability, moving from seeing it as pure chance to reading it as a reflection of the weighting, the robustness of these broad versus thin continuation paths. You know, this whole idea that reality unfolds in discrete clicks raises a huge, huge question. If everything happens in these tiny steps, then what even is time itself? Are our most precise clocks just measuring some smooth background flow, or are they actually counting the fundamental ticks of reality's clock? That is exactly what we're going to explore next time. That's all for this explainer. Thanks so much for joining me. I'll see you next episode, and as always, stay curious.